Hello class. Uh, this is the NMAT B, how do I get in there? Video lecture 2.0. A day or two late from my promised date. I'm sorry about that. I had a really busy weekend. But yeah, here we go. We have again a supplement to the lecture I had. Remember again, this is only to fill in gaps. Hopefully you were able to come to lecture and look through your textbook. Well, I'll step back just a few sections back from 12.1 to 12.4, I believe. It may seem like we're going through all of these things so quickly, which is why I think this is useful so you can take your time and read through this and play it back at your own pace. I also hope that you can, solve as many examples as you can find in your book as well, just to reinforce some of these new concepts. So we've discussed orthogonality of functions. And the idea was to determine, we wanted to, again, find a way to expand any function as a linear combination of an orthogonal set of functions. Now, we define orthogonality. We use a different pen. I think the color here is not so clear. We define orthogonality of two functions. If we had phi n and phi m, the inner product in an interval AB is defined as phi n of x dx, the integral of that. And if this is 0 for n not equal to m, we have an orthogonal set. Okay. We studied the Fourier cosine series, Fourier sine series, in which phi n were all trigonometric functions. I don't need to go into that for this lecture, but I probably will come back to it at some point if we want to solve more examples. But for this lecture, I just wanted to refresh your memory on where we are so far. There are a lot of interesting things that we can do with. So once again, when they are orthogonal, by the way, we have linear independence. And in theory, if we have a complete set, then this is possible as long as our series converge. And we also discussed conditions for convergence for a continuous function and for a function with a finite discontinuity. So look through your textbook and your notebooks and confirm that you remember all of that. What was I going to say? So this idea of expanding functions in terms of an orthogonal set, again, we've seen how important, how interesting it is in the use from sections 12.1 to 4 of expanding series, of determining series expansions. Like I said again, we looked at the full Fourier series. We've looked at the Fourier sine series. And we've looked at the Fourier cosine series. We talked about full expansions, full range expansions. We talked about half range expansions. Then we slowly tried to, we didn't develop it in class, but your textbook shows a very, very nice proof of the complex Fourier series as well. There was one little thing I didn't tell you about the complex Fourier series I just want to quickly touch on. I told you that if you wanted to expand using this new set of complex functions, orthogonal complex functions, sorry. If I use, okay, I'll explain this in a second. I can go from minus infinity to infinity. And then we define Cn as 1 over 2p minus pp f of x e to the negative I n pi x over p. I told you that you had a new set of orthogonal functions, and I claimed that this was the inner product of f with this, and obviously this is the divided by the square norm. And I didn't want to get into this, but for those of you who were wondering how this works for complex functions, I'll quickly, and by the way, you note here that our orthogonal function is different from what it looks like in here. This is positive, this is negative, exponential. The reason for that is, well, the reason for that comes from the derivation that you see in your textbook. But how that plays out in determining inner product is what I want to show you here. If I have two functions, f and g, and I find the inner product of these two functions, if they're complex functions over an interval ab, it's defined as the following, where this is the complex conjugate of f of x. Okay. In the case of, if I have a plus ib, its complex conjugate is a minus ib, right? Just look at the imaginary part and take the negative there, right? For the case of exponentials, f of x equals e to the I 2 n pi x over p has a complex conjugate of e to the negative I n 2 pi x over p. I'm not going to test you on this. I don't expect you guys to know how to deal with complex functions or complex variables, but just for those who are curious. So if I wanted to find the inner product of two of those, I told you that it can expand as, using the new set of orthogonal functions. So I wanted to find the inner product of one of them, I n pi x over p. Or I might put in 2 here, sorry. And e to the I m pi x over p. It will be defined as, for an interval ab, it will be defined as e negative I n pi x over p, e I m pi x over p dx. Okay, and actually we know what this interval is. We don't need to use an arbitrary variable here. We were looking at minus p to p for this kind of form. Okay, so we can show indeed that they are orthogonal just by doing this integration. You get negative p e to the I m minus n pi x over p dx, which is simply e to the I m minus n pi x over p. Or if you prefer, actually, this might make it this might be a little easier to see. Negative p to p, break to the cosine, n minus n pi x over p, minus I sine m minus n pi x over p dx. Okay, is it clear? I see it. Okay, so this is an odd function. I'll get 0 considering the symmetric interval I have here, limits I have here. So I'm really just calculating this right here, dx. Okay, and that's easy. Just simply sine divided by p over pi minus n, going from minus p to p. Plug in those limits. Obviously, I get sine of an integer pi x, which is always going to be 0. Okay, so it's 0 when m doesn't equal n. If m equals n, then I get ein pi x over p, ein pi x over p, which is e to the in pi x over p times e to the complex conjugate of that n pi x over p dx. So this times this is e to the 0, right? Minus p to the p 1 dx. E to the 0 is 1, which is just what am I doing here? Let's see what happens here. Am I getting 0? P to the negative p. Oh, sorry. Okay, so that's 2p right there. Okay. So my square norm is 2p. So my norm is square root of 2p. Okay, so you see how that works now, and that was, this 2p was the factor that I had outside of my complex Fourier series expansion. If you remember, we had f of x equals 1 over 2p integral of minus p p. So this was from that square norm. Okay, so that's to satisfy your curiosity. For those of you who had to go through this that weren't interested, sorry. Just a brief detour. So we went through 12.1 to 12.4, developed all of these ideas, and I was on Friday, or was it Wednesday, we started discussing a new set of this particular form of differential equations, and we got into understanding a very interesting property of this differential equation. What we saw was that they tend to yield orthogonal sets of functions as solutions with the appropriate boundary condition. The boundary conditions have to be correct for this to work. Orthogonal sets of functions. Okay, I'll go back to the example that we solved in class because it just is a really good. I think it's this. Okay, and it was for y 0 equals 0, yl equals 0, whatever our interval is. If you remember, we solved this using characteristics equation d squared plus lambda equals 0, which meant that d was plus or minus square root of lambda I, and that's why we had y of x equals c1 cosine root lambda x plus c2 sine root lambda x. Okay, applying this boundary condition tells you, so if I plug in x equals 0, I get 0 equals c1 cosine of 0 is 1 plus sine of 0 is 0. So c1 has to equal to 0 for this to be true. Okay, and if c1 equals 0, then we have only the sine term left because this goes off. So y of x equals c2 sine root lambda x And then the second boundary condition helps me determine the next constant. And what we saw was that it led to sine root lambda L. Okay, what we saw was that we could have had a trivial solution with C2 equal to 0, right? In which case, all our solutions y equals 0, which is kind of like a, I mean, it's a solution, it's a trivial solution, but it's not interesting enough. It's not interesting. Let's look at the case where this is 0. Okay, for that to be 0, we saw that we needed to set square root of lambda to be n pi over L. Right, that way I have sine n pi. Right, and we know that that's always equal to 0 when n equals an integer. Okay, and so we went ahead and so that led to the idea of setting. So we have an infinite number of lambda that can satisfy this differential equation and boundary condition. So we have our eigenvalues, is what we call them, as n squared pi squared by L squared, and the eigenfunctions corresponding to those eigenvalues as sine n pi x over L. Okay, so this example was shown to illustrate how boundary value problems often turn out, well, boundary value problems of this kind of form. You have a given Sturm Louiville kind of equation, and I'll show you again how this was. I can identify as a Sturm Louiville equation, and with the appropriate boundary condition, we end up having eigenfunctions that are orthogonal. And if you recognize, this is the same set we used for the Fourier sine series. Orthogonal and linearly independent because of the orthogonality, and then a corresponding eigenfunction. Okay, this differential equation, I wrote it in class as Ly equals negative lambda y, and I was telling you that this kind of eigenvalue problems you see a lot of, right? It's again, okay, I'll get into that in a second. There's something special about the operator of Sturm Louiville differential equations that I want to talk to you about real quick. But just remember, if I have a differential equation of this form, it's a eigenvalue problem that, and if given the right conditions, that they yield again the orthogonal sets of functions we talked about. Okay, I will go on with that. Your book posed this as the general form for your Sturm Louiville problem was posed as follows in your book. Lambda px, that's your weight function that we talked about in class. If I wanted to write it in the form Ly equals negative lambda x, I could, right? Just pull out this term to the other side. Right, so Ly is r y prime prime plus r prime y prime plus q y. Okay, and if you remember the previous example, Ly was just y prime prime. So r equals 1, r prime is 0, q is 0. Okay, so that previous example was a Sturm Louiville kind of example. Again, I'm just trying to use this form for convenience, and you see how useful it is in it. in a bit. It's just an arbitrary differential equation I'm calling L. Arbitrary differential operator. Okay, so we also talked about, so this is the general Sturm Louiville form. You may have seen it this way in your textbook also. R y prime plus q x plus lambda p x y equals 0. Okay, so this kind of Sturm Louiville condition, differential equations, coupled with the boundary conditions that we showed in class as well. A2y prime of A B plus B2y prime of B. This is y. Coupled with these boundary conditions yield linearly independent and also orthogonal sets of functions corresponding to unique eigenvalues. Okay, and we're getting to some interesting point. Actually, before we get to that point, just to again remind you what these boundary conditions are. It's a homogeneous, two homogeneous boundary conditions. Homogeneous being equal to 0 on this side. It's a combination of a value at each end. Alright, so they're separate boundary, they're not a mixed boundary condition, because you have one in terms of the lower limit A, another in terms of the upper limit B. Okay, so if you can have these kind of conditions, you satisfy Sturm Louiville. It's a Sturm Louiville set. It's a Sturm Louiville differential equation and boundary condition set. If you look at your textbook on page, see. If you look at your textbook on page 649, your book tries to show you how it was trying to prove that you had indeed an orthogonal or orthogonality of the function solutions. And the condition that I want you to focus on is condition 8, right at the top of the page. For it to be true, for orthogonality to hold, the boundary condition states, or there was a boundary term. And I write it down, it's kind of long. Just look at it yourself. It shows RB blah 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 on the minus RA something. Okay, and because of the boundary conditions, we had this equal to 0, and then you had orthogonality on the left hand side equal to 0 for that reason, which led to orthogonality. Is this clear? Yes, you can see it still. Okay, I hope. Okay, so one thing I wanted to quickly highlight is that R of B and R of A could also equal to 0. Right? In other words, when I had my Sturm Louiville form, dx R y prime plus q y equals negative lambda p y. If this R here is such that, if this R of x is such that the limits then we can determine a natural interval for which our differential equation is a Sturm Louiville differential equation. Okay? So, let's try and visit, and then we also talked about one more thing. We talked about how we can pose if we have any second order differential equation of this form. Let's call it b of x. We can make it into the Sturm Louiville form by going through, oh, this was called A and B. We called, and even if this is not the first derivative of this, as in the case of the Sturm Louiville problem, we can still get into that form. We divide this by A and then multiply it by the integrating factor to lead us to the Sturm Louiville form. As an example, we're looking at the Bessel equation, x squared y prime prime plus x y prime plus, I think they used the parametric form, which we didn't really discuss, but sorry. Something is wrong there. We didn't really discuss, but we that's what I missed. But we do know enough to do it. We solved some examples using substitutions. If I chose z equals alpha x, for instance, then my dz equals alpha dx. All right, plug that in there. Well, then my dy dx is just dy dz times dz dx, which is alpha, and my d squared y dx squared is d dx dy dx, which again gets you an alpha d dz. Now that alpha dy dz, which is alpha squared d squared y dz squared. Okay. Plugging those values into our original equation gives us x squared y prime prime. Now our prime primes are in terms of z, alpha squared, okay, which is what we just derived, plus the one from here was alpha x, plus alpha squared x squared minus n squared y of z equals 0. And if I just replaced it with the variables we just substituted, plus z y prime plus z squared minus n squared y of z equals 0. So you can clearly see that this is the Bessel equation form that we are familiar with. This is Bessel's differential equation of order n. Okay, our solutions for this would be j of z, jn of z, and well, depending on whether they're separate by well, if we're looking in the case of n being integers, jn of z and yn of z. Okay. If they're not integers, then it'll be jn and j negative n, like we looked at in class. Okay, so this Bessel form right here can be converted to Sturm Louiville form by doing the same trick. I divide by x squared, identify this is my b, this is my a, divide by x squared, I get y prime prime plus y prime over x plus alpha squared minus n squared over x squared y equals 0. Okay, so our integrating factor was e to the integral of b over a, which is 1 over x dx, which is e to the natural log of x, which is x. So I'm going to multiply through by x, and that gives me x y prime prime plus y prime plus alpha squared x minus n squared over x equals 0. Okay, which I can write as dx x y prime. You see that? If I differentiate once, I get x y prime prime plus y prime plus I'll write it this way: negative n squared over x y equals negative alpha squared x y. You can identify this as my eigenvalues and this is my weight function. This is my q of x. This is my r of x from the Sturm Louiville problem. Okay, so again, this is the reason why we try to cast it in the Sturm Louiville form. That way we can easily identify our weight functions and all of its other functions. And since I now know that p of x is x, I can say, oh yeah, I know my orthogonality condition. Let's just use a to b for now. X is the weight function, j alpha x is the solution, right? It's what we just derived. J n, a different alpha, let's call this alpha n, or alpha I, alpha j x dx for I not equal to j equals 0. So this is the orthogonality condition for Bessel's function. Okay. So another important thing that we can get is that since we know these are the orthogonal solutions, or these solutions here are all orthogonal based on this and based on what we showed, the interesting property of Sturm Louiville equations, then I can expand any function as a combination of the Bessel functions. Okay. Sorry, let's not do that. Let's call that J, my goodness, let's call this, sure, let's call this, keep it as n as an index, but the n is on alpha, not on this. It could be any j, depending on what my original form is. Let's call this j mu, as we've always done in the past. Okay? So we can expand it as orthogonal set of functions, where the function is the solution to the original eigenvalue problem. We showed also for Legendre polynomials. We showed that for this form, we showed that this was r prime, and this here was our lambda, and our weight function was 1. Okay, just making sure you could read what I'm writing. Alright, weight function is 1, and as a result we can go from some limit again, go from one solution okay. In this case, our eigenfunctions, let's say L and, well, doesn't matter, nm equals 0 for n not equal to m. Okay, and corresponding for Pn, our corresponding eigenvalue is n plus 1. For Pm, our corresponding eigenvalue is m plus 1. Okay. Now let's talk quickly about the limits. How do you determine limits? Like I said before, one of the more important things to worry about is your boundary conditions in Sturm Louiville problems. If the boundary conditions satisfy the form that we showed earlier, then we have Sturm Louiville problems. Sometimes we don't need boundary conditions to satisfy for us to have Sturm Louiville problems, right? Like I showed you, if I have a situation where Ra equals Rb equals 0, then we have already a natural interval for that differential equation. In this case, R is 1 minus x squared, right? The root of that equation is x equals plus or minus 1. Okay? So clearly, if I go from minus 1 to 1 as my interval, then R of -1 and R of 1 gives me 0 also. Okay? Does that make sense? So this is my natural interval. So for the Legendre polynomials, or Legendre differential equations, this will be my orthogonality condition. Again, the weight function is 1. Function is 1 is why we have this form. For the norm, the square norm of the Legendre polynomials, I think I gave you that integral in the past. Square norm for any of them is just simply two over 2n plus 1. Okay? Okay. So for the Legendre polynomials, again, you can expand any function because they're orthogonal as the following. Okay. So this is an interesting thing we're getting to see here now. Not only can we expand in terms of sines and cosines, right? We can do expansions in terms of sines. So phi n could be what we saw for Fourier cosine series. It could be what we saw for Fourier sine series. It could be what we saw for the combined series. It could be what we've seen for the Bessel functions. It could be what we've seen for the Legendre polynomials. Okay, again, remember the orthogonality conditions for each of this series. Okay, so the Legendre polynomials, Legendre functions, the orthogonal Legendre functions were easy to work with. The Bessel function, on the other hand, a little bit messy just because of the intervals that we're working with to make them Sturm Louiville. We had said that we had a form x squared y prime prime plus x, or when we recast it to the form, one second, when we recast it to the appropriate Sturm Louiville form, it was x y prime prime plus y prime plus alpha squared x minus n squared over x y equals 0. Okay. So your book shows and they covered this really well. If you look at the, remember what we're talking about with the natural intervals. This is my R. Clearly, if x equals 0, R of 0 is 0. Okay, so we have some limit, lower limit that we can work with. So I can always define my orthogonality from 0 to b because we have this working. In the previous case with Legendre, we had two limits that worked well, so this wasn't an issue. Now we have to figure out what b we can choose for us to have a Sturm Louiville problem, for our boundary conditions to work. Okay, so we had jn alpha I x jn alpha j x dx. Okay, if you go to page and first of all, remember the conditions that we want to see is of the form a1, say, excuse me, jn x. In this case, since we're using the expand the parametric form, alpha x plus b1 jn prime alpha x, well, jn prime, the derivative of that function this time will bring out an alpha from chain rule, okay, equals 0. Is as long as this satisfies, sorry, alpha b, so the upper limit, as long as it satisfies this kind of boundary condition, we have a Sturm Louiville problem. Okay, so again, your book here on page 654 shows you a nice way to determine the square norm for each of the different kind of boundary conditions you may see. So if I have, take a look at from cases 1 to 3, actually they cover it very well in your book. You have 3 cases for this kind of boundary condition for which you can determine your square norm. I won't bother trying to rewrite that. There's a more important point. I mean, this is very important, by the way, but there's another important point that I would like us to go through, and that's the one I was trying to get to you guys when I said it was going to blow your mind. It turned out I didn't quite get to you guys as I wanted to, but here it goes. Wherever you are, whatever you're doing, this is very important. You know, grab a glass of wine. You know, if you're a beer kind of person, grab a beer, turn up some soft music, enjoy this. You know, invite your boyfriend, your girlfriend. This is fun. This is gonna be really good. Okay, so we had said that we were studying differential equations of this form, negative lambda y. In the general case of the general Sturm Louiville problem, we were looking at something like this. Okay, so for the Legendre differential equation, for the Bessel differential equation, for the other ones that we did with sinusoidal functions as solutions, we're able to show that we could expand solutions. We could expand our function y of x equals, or any function y of f of x, let's say, equals cn by n of x, where these are your eigenfunctions. Right? So what we want to see is how we can apply this idea to solving something like this. Okay, so if I'm telling you, if I give you a differential equation of this form, right? So for example, the first differential equation we were looking at, if I said y prime prime equals sine x. Is that a good example? Hold on, let me see if I can find. So this is one of those parts of the video you can skip right through. I thought I had a good example. Turned out I'm doubting myself here. Sin x will work, but I messed up right here. Well, before we get to that, oh, why not? So if I have L as y prime prime equals sin x, for example, this is an easy one to solve, right? And I'm giving you the same conditions, say y0 equals 0, y of L. Let's say y of pi equals 0. Then, I mean, this is really easy, and that's why I've been thinking of using, whether I should use the example, but I'm thinking it may actually make sense to try something simple that you guys can verify. If I integrate this twice, right, this is an easy one to solve. Y prime equals negative cosine x, y equals negative sine x, and we have a constant here. We have a constant times x here. Okay, so this is a general solution. This is an easy one, so we don't need to. Why am I doing this? Why am I doing this? Okay. Well, this is the solution to this from the technique we know. What if I complicate this a little bit, and to find out the constant, you plug that in. What if I complicate this a little bit and say y prime prime plus 2y equals sine x. Okay, we have we can solve the homogeneous form, which is using the characteristic equation y equals c1 sine root lambda x, or sine root 2x, sorry, plus c2 cosine root 2x plus some particular solution. Okay, and we know from the first class many methods of solving that particular solution. Let's say I used the method of undetermined coefficients. I know that yp is of this form: a sine x plus b cosine x. Why did I choose that? Because I know that once I differentiate once and twice, I'm getting sines and cosines. If I plug this in, pardon me if you know this, if this is boring you, but I just want to emphasize something real quick. Plug a sine x plus b cosine x into this, I get a the sine x one, I differentiate twice, I get negative sine x back, plus b, the cosine x, differentiate twice, I get negative cosine x back, plus 2a cosine x sine x plus 2b cosine x equals sine x. Okay, so for this to work, minus a sine x plus 2a sine x plus 2b minus b, which is b, cosine x has to equal to sine x. So a sine x equals sine x, so a has to equal to 1 and b has to equal to 0. So sine x is our solution. Wow, did we really have to go through there? Okay, so sine x is our particular solution. And it turns out then that our general solution is y equals, what did I have right there? C1 cosine with 2x plus C2 sine for 2x plus sine x as my general solution. Okay, this is easy, right? And I'm sticking with this example, and then I can find out this constants using this term, this boundary condition. For now, I won't solve that. You guys can complete that on your own. What I want to show you is how we can use this idea that we've developed to solve the differential equation. Okay, so one assumption is, or one thing that we now understand is, the solution is of the form Cn, a linear combination of the eigenfunctions. Okay, and what we were showing in class was that if I plug this into my differential equation problem, I have the following. Okay, I'm going to use this, the general case of when I have a weight function. Okay, I can pull this in because this is a linear differential operator. This is just a sum of functions. So this equals n equals 0 to infinity Cn Lyn. Some of you can skip through this if you want. It's the final result I want you guys to see. Okay, and this Lyn here is just this here, right? What that tells me is that I can expand my function f of x as Cn negative lambda n rho of x y of x. Okay, why am I doing this? Even though we know that, because we originally said we could expand y of x as a similar kind of expansion, but without this. But we're trying to determine the coefficient Cn. We can't determine it from y of x because we don't know what y of x is, but we know what f of x is. So we can apply the orthogonality trick that we've now mastered, I hope. If I take the inner product of f of x with respect to one of the orthogonal functions, and my inner product here is inner product with respect to 1, as in it's defined as the weight function is 1, okay, for this inner product. So let's just call it star. This is a weight function of 1 for the inner product, equals sum of n equals 0 to infinity Cn lambda n. Let's put a negative sign out here. and then rho x y yn x ym x. Again, this is the inner product with respect to a weight function of 1. So I can remember that every term in here goes to 0, right? If we're doing this here, is simply, sorry, that last term, that last inner product here is worth looking at a little closer. It's integral a to b rho x yn x ym x dx, which is the orthogonality condition for a general weight function, rho, or px, sorry, px. Okay, this is a general orthogonality relation. So it goes to 0 for every n not equal to m. Okay, if n doesn't equal to m, this goes to 0. So all I'm left with is f of x ym of x equals c m lambda or negative lambda m and the square norm of m. Okay, so my ink is dying. So my coefficients can be determined as Cm equals f of x ym of x inner product with respect to 1 divided by negative lambda m square norm of m. Okay, this is a very interesting result, because since I now know my Cm, I can go back and determine my y's of x, which I had called the following. Okay, I now know my Cm in terms of f of x, the known function. So f of x equals sum of n equals 0 to infinity. Cn, which was, wow, why did I wipe that off? Cn, which was f y n of x norm of yn of x y n of x. Okay, this is our Cn and this is the yn of x. Okay, so we have a really nice handy way of determining our solution. Now I want us to see how this works for the example we gave earlier, even though it looks more complicated. So what I want to do is 58:55. I don't want to go over an hour. I'm going to stop and start right back again.